All right, today we're taking a look at section 4.2, logarithmic functions, and some ways of solving them. We'll look a little bit more applications actually in a different section, even though the title is right here. So the first thing I'd like for you to remember before I even go into any other slides, is there was a section that we did back, oh my goodness, it feels like it's a couple chapters ago even, where we talked about something called inverse functions. Does that phrase sound familiar? Inverse functions. One of the things we did when we talked about inverse functions is we switched x and y and we solved for y. Do you remember that? That was sort of a technical way of processing through that. And we didn't talk at length, although you did have some homework problems that emphasized the fact that when you did that, certain things happened on the graph, domain and range switched places, stuff like that. So what we're looking at in this section, logarithmic functions, are the inverse functions of the exponentials that you looked at in section 1. So a lot of the things that we're going to look at as we move through this section and the next couple sections afterwards, you're going to feel like, wait a minute, isn't that kind of like exponentials? And the answer is going to be, yes, it is, because they're actually just the inverse functions. All right, so to get started, let's actually define what a logarithmic function looks like. An equation for that would be f of x equals log. The little a is actually lower than the log line. It's not written next to log, it's a subscript. And then the x afterward is written on the same line as the log. Okay, we read this as log base a of x. A couple of conditions on the a. The a value cannot be 1, and the a value must be positive. Now you've seen those restrictions before. Those were the exact same restrictions we had on the base of an exponential. Base cannot be negative, it has to be positive, right? And it can't be 1. Now, in your mind, hopefully it's been fresh enough since you saw the video and remember it. Do you remember on the graph of the exponential what the domain was for an exponential graph? You're right. Ainsley said it was everything, and she's exactly right. Well, remember I told you domain and range switch, because x and y switch. So if the domain for an exponential is everything, then the range for a logarithmic function is everything. That's the range. So then what was the range for an exponential function? 0 to infinity. So since that was the range for the exponential, that will be our domain for our logarithmic. And we will look more at graphs later to sort of verify these pieces of information. But they are switched. Now, if you were to grab your calculator out and you were to look for a log button, you would find one. But the log button in your calculator is not just any log. It's what's called the common log. So when you press log in your button, the log button in your calculator, you're actually finding log base 10. So as we're working with this, when we see just log, we may in fact change it to write the base next to it just to remind ourselves that that's actually the base that we're using. It's called the common log. Now there are ways, and we will discuss them today briefly, just in case you see anything that asks you to do some approximations on your homework, of how do I get log base 5 in the calculator, though? There's a way to do that. I'm going to show you how later in the lesson today, just as a calculator note, basically. But realize that the log that you're using in the calculator is log base 10. There's another log in your calculator. It doesn't say log, it says ln. ln is the natural log. Now, for those of you who've ever done any sort of language course in another language, you've probably encountered the fact that English does their adjectives and verbs different than many other languages. We say natural log, but if you were working with Spanish, they would say log natural. They put the adjective after the verb. So if you were to switch the order, log natural, there you have the ln, and that's where that's coming from, okay? So it's the log natural, the natural log. So anytime you see ln, it means that you have a log with a base e. And we talked last time that there's an approximation for e. Do you remember what it was? 2 and it's 718 if you use 3 decimal places. I imagine that's what I put in that slide before. 2.718 approximately. Okay, so it's this funny irrational number as a base. And as we look at the graph, we'll actually talk a little bit about real life situations that have this sort of phenomenon occurring. Log functions, natural log functions, these are actually really common in how things really happen in life, and we'll give you a couple of examples when we get there. All right, before we get there, I want us to do a little bit of practice simply in converting. How do I go from a log function to an exponential function? Because I just told you that somehow you can switch x and y and solve for y, right? Like that's the process we went through for inverses back in the day, you know, like a month or two ago. I mean, it's been a while, is that we switched things around. Well, there's a process by which to switch between logs and exponentials, and that's what we're going to look at first. Now, the directions on this simply say to rewrite. We're not asking us to find what a letter, a variable equals. We're not asking us to solve anything. We're just asked to rewrite. So if you write the first one down, I'm going to show you a visual for how you can rewrite a log function. I don't know about you guys, but for me, I'm a very visual person, so images that I've seen and things like that, they stick with me a long time. One of the things that I remember very specifically from my youth is that we had a Bible quizzing program in the denomination I was a part of, and I memorized scripture in such a way that I could tell you where that verse was on the page. I mean, that's just how my brain works. I have a daughter, she's in the same quizzing program. That doesn't resonate with her at all. Everything she does is auditory. She can hear it. They've got songs, these little jingles and whatever, and she memorizes everything she does by auditory learning. So I'm going to show you a visual. For some of you, it will probably resonate. For others of you, you're going to be like, and that's okay. Okay, so we all learn a little bit differently. What I'd like for you to do is I'd like for you to circle the 3, and I'd like for you to draw an arrow around where the final arrow lands on the 81. This image looks something like maybe a scorpion tail. Did anybody shudder when I said scorpion? You are in Oklahoma. If you're here long enough, you will see one. It's creepy. Probably not right now. The temperatures outside are not really scorpion weather just yet, so, All right, so here's the way this works. The circled part is where we're going to start. That's the base of this log. It will become the base of our exponential. Okay, the word base is used in the same way in both cases. It is the base. If you follow the arrow around to the other side of the equation, you encounter the number 4. That 4 is your exponential for your base. And this will equal where you land, namely 81. And this process can be used on all of these problems to rewrite these equations. You always start with the base, you go to the other side of the equation, and you land right back next to where you started. Now, this is a true statement. 3 to the 4th actually is equal to 81. If there were a variable in this, we might actually try to solve that next, given different directions. But all we're asked for right now is to simply rewrite, and we've done that. So I'd like for you to try your hand at the second one. Now, you have to be aware of what the base is first, because it's not there. What's the base of this log? It's a 10. Right? It's a common log, so it's a 10. So I would encourage you to put the 10 in, circle it, and start there. So take just a minute or so and attempt to rewrite this, and we'll make sure everybody's on the same page. Most of you look like you're finishing up. This is what my curved arrow, if you will, would look like. You should have had a base of 10. What was your exponent? Z, good. And then it equals 1,000. And we aren't asked to do so on this one, but it would be pretty straightforward to figure out at this point what Z equals, right? What would it be? It's 3. Yeah, it's the power of 3. Okay. So in this set of 2 questions, we worked with log functions, turning them into exponential functions, or log equations to exponential equations. What do you suppose we're about to do next? The other way around. We're going to start with exponentials, and we're going to turn them into logs. Okay? So same directions, write an equivalent, but the part that changes is it's an equivalent logarithmic equation. Now, Your circles and your arrows, they work the same way. We always circle the base. What is the base of the problem in part A? It's a 10. So I'm going to circle the 10. And I'm going to draw the arrow to the other side and land right next to where I began, which means ending at the 5. Now, as I write this one, I have to make it a log equation, so I'm introducing log into the function. And as I'm moving from left to right, the base is still the base. Our base that we circled in the problem here was the 10. So our base for our log here will be 10. Following my arrow around, what do I encounter next? The W. So the W will come next on the same line as the log, and this will equal where I end. Where do I end? A 5. Now, there's another way that this could be written if you were sort of checking the back of the book for answers or comparing with a partner or something like that. How else could you write log base 10 of W equals 5? Without the 10, exactly. Yeah, you could write it as log W equals 5. And that would actually be the exact same expression based on the fact that common logs have log base 10. Okay, B looks a little different. You've got two options. You can rewrite it so that you move the exponential part to the other side. So honestly, if I were working with this, I probably would do this because then my circles and my arrows look just like the ones I did before. I would circle my base B and draw my arrow around. You certainly don't have to do that, right? You could circle the B where it is and draw the arrow to the other side of the equation and around. Your arrow just looks like it's going in the opposite direction. There's nothing wrong with that. Just visually it looks a little different. Okay, got to go to the other side of the equation before you land at the exponent. Either way you do that, you're going to write the word log down next. What's your base? B. So that's my subscript. What would I write next? Z, the other side of the equation, and then this will equal the K for the exponent. Okay, so practice done with rewriting. We're going to go one step further with our next questions. We're going to use this kind of rewriting to actually solve some equations. Okay? Now, they aren't actually equations, so I will say that right off the bat. These are going to be expressions, but we're going to make them equations. So let's take a look. The directions simply say find the indicated value. I don't know about you, but if I looked at log base 216, and I know I can't use my calculator because it doesn't have a log base 2 in it, right? I mean, like, that's the deal. It just doesn't. The way it's written right now is not very familiar to me. But exponentials are more familiar than logs. So what we're going to do is we're going to write that this equals, and you can pick your favorite variable. Mine's going to say equals x. And if I put that equals x in, it allows me to be able to rewrite it just like I did on the last two slides, right? I can switch back and forth between notations. So what would I do if I wanted to change this into the other notation? Circle a 2 and draw my arrow. How can this be rewritten? 2 to the x equals 16. If you can see it right now, that's fantastic. What is the value for x? It's 4. If you can't just look at that and see it, then what you would do next is you would try to get the same base on each side. The left-hand side just already is as simple as it's going to get. It's a 2. Right? I can't change that really and make it any better looking. It's as simple as it gets. But the 16 could be rewritten as 2 to a power. And in particular, you could play with your calculator if you needed to, if you weren't sure. Eventually, you would find out one way or another that that power would be a 4. Okay? 2 to the 4th would be 16. Part B on this slide is the hardest one. Part of it is because of the fraction. But there's another thing going on in that one that makes it difficult as well. So let's take a look next. We're going to start out with saying equals a variable so that we can rewrite it in exponential notation. So I'd like for you to take a second, rewrite the exponential notation, and then we'll reconvene and we'll solve it together. Okay, so you should have started with the 1/5, drawn your arrow, and your exponential notation should look something like this. 1/5 to the x equals 25. Is everybody good with that? Awesome. All right, this problem is a lot like what you encountered back in section 4.1. Both sides of it can be rewritten with the same base. All right, what would the base be that you could write both sides to have in common? 5, right? One of them is a 1/5, the other one's a 25. If you were to factor it, it would be 5 and 5, right? So what we're going to do is we're going to rewrite both of these as 5 to some power. So 1/5. 1/5 is 5 to what power? -1. Now I still have, oops, hang on. I still have the equals, or the x at the exponent right there that's still there. So let me put that back in. So it's 5 to the -1 to the x. We'll deal with that in a minute. What are we on the right-hand side? 5 to what power? 5 squared, 5 to the 2. On the left-hand side, when I have a power to a power, how do I combine those? Do you add or do you multiply? Do you remember on this one? You multiply on this one. You add when there's two bases with exponents, and this has just got one base. So this is 5 to the -x equals 5 to the 2, 5 squared. Okay, the whole goal with exponential equations is if the bases match, you can pretty much ignore them. You're not canceling them. Please don't mark them out like you are. That's not appropriate. But you are ignoring them, because if the bases match, then the exponents must match as well in order to make the equation true. So instead, now, this equation focuses only on the exponents. I now need to know where is -x equal to 2, and what x value would do that for me. Yeah, x equals -2, right? So this expression would actually equal -2. All right, so I'm going to pause right here for a moment and say, wouldn't it be nice if our calculator could at least verify for us that these answers are correct? And the answer is that it can. We'll talk more about this later formally, but let me talk to you about how you verify with your calculator. Now, even as I tell you this, I'm going to tell you that the work that we just did, at least a good bulk of it, that's what I would expect to see on written work that you do. So what I'm about to show you is a calculator trick to verify only. It's really nothing else, okay? So if you will grab your calculator, if you have it, and if you don't, that's totally fine. I'm going to do the first one together, and then you guys can verify the other ones after that, if you prefer. So we'll take the first one, log base 2 of 16. And I'm going to show you how you can use this and use your calculator. You can change change this into the expression log 16 over log 2. This actually has an official name. It's called the change of base formula. Basically, we've changed the base from 2 to being a base of 10, and we've rewritten them. It does matter that the log 16 comes first, that is in the numerator, and the log 2 comes second into the denominator. And if you put that into your calculator, just verify real quick that you get a 4. Julia nodded. Anybody else have theirs and verify? Yeah. Okay, I've seen several nodding heads. And you can do the same thing on the log 25, right? This would be log 25, and you would divide it by log 1/5. Okay, so you can verify that as well. This isn't a necessary way of solving these, that we will encounter one in a little bit that we will need this in order to get an approximation for, but it would be a way to verify. And in particular, C and D you could directly do in your calculator as well, right? Because they are log and they are natural log, and those are both buttons you have. But I'd like to show you why they work the way that they actually do work. So if I were to set this equal to x and do the same thing I've been doing, I'd have a base of 10, correct? How would this get rewritten if I were to rewrite this in exponential form? Right. 10 to the x equals 10. And what would x be? 1, right? Of course, your calculator can verify. You can write in log 10 and press enter, and it's going to tell you 1. But this actually has ramifications that are even better. The base was 10, and the inside of the log was 10, right? And that's actually going to work no matter what happens. Let's say that the base were 5, and the inside of the log were 5. The base were 150, the inside of the log were 150. It will always be the answer 1. So in particular, when these match, the answer is 1. And we'll talk more about that property. I think it's in section 4.3. All right, natural log 1. Again, you can put this in your calculator. It's going to tell you what the answer is, but let's take a look together at the y based on the exponential components here. If I set this equal to x, what's the base of this log? E. So this is the same as saying log base e of 1, not natural log e base e of 1. It's log base e of 1 equals x. And if I were to rewrite, what would it look like? E to the x equal 1. What would I have to raise e to get 1? 0. And again, that's actually true no matter what base I had, right? If this were base 5, or this were base 10, or this were base 152,967, right? The log of any base of 1, any base of the 1, is going to equal 0. Again, another property that we'll encounter and talk a little bit more about later. I'm going to shift gears with you a little bit, and we're going to take a look at the graphs of logs and their relationships to exponentials. Sorry, duplicate slide. There we go. What I'd like for you to draw first is from your memory, and if you don't remember, just pause and I'll draw my example up in a minute. I'd like for you to draw the graphs that we did back in section 1. Log base a, I'm sorry, not log, y equals a to the x. In one case, the a value is bigger than 1. In the other case, the a value is between 0 and 1. So just give a real quick sketch of what you remember. And if you don't remember, just hold tight and we'll draw it together. Compare what you have to a rough estimate of what I've just drawn on the board. This isn't very nice on the very end over here, but it looked something like this back in section 4.1. It's your exponential graphs. They're reflections of each other over the y-axis, right? If you reflect from one graph to the other graph, you switch back and forth. And it's all based upon whether or not the number is either bigger than 1 or between 0 and 1. Okay, so what I want to do is I'm going to change colors, and I'll draw these on another graph here in a minute as well. And I'd like to draw the log graphs that correspond to them. So on the first one, this is log base a of x, where again, the a value is bigger than 1. And on this graph, it looks like this, roughly speaking, crosses at 1. And on my other graph over here, looks something like this. When the a value is between 0 and 1. And we didn't talk at length when we did inverse functions, but you did have some examples in your book that showed you that when you draw a graph and its inverse, they are reflections over the line y equal x. And if you were to draw the line y equal x in here, that's not very good. I'm going to try one more time. That's better. Something like that. Do you see the reflection? If we were to fold it along my dotted line, the white graph would land on top of the yellow one. or vice versa. It's easier to see that with the first graph, but it's also true for the second graph. It's just harder to see it because they are crossing one another. If they were drawn well, mine are not drawn exceptionally well this time around, they would cross each other and it would have perfect images that when you flipped the top piece that's white down, it would land on the bottom piece that's yellow, and vice versa. These are reflections over the line y equal x. Now, I'm going to take the next slide and I'm going to redraw just the yellow pieces. So feel free to redraw if you need to. If that doesn't bother you, you're fine. So the graphs of the logs look like this. And we're going to analyze some pieces of information. They do in fact cross the graph much like they did with the others. All right, so what is the vertical asymptote you see happening on these graphs? How about the first one? What is your vertical asymptote for the first graph? Can you see a line that it gets really close to and doesn't touch? Yeah, the y-axis. What's the equation of the y-axis? X equals 0, very good. And actually that's true for both graphs, isn't it? It really is. One of them is getting closer and it's getting is an increasing graph. That's the first one. The other one is getting closer, but it's a decreasing graph. At least on the left-hand side, it gets closer. What's the x-intercept on our first graph? Remember, it's a point. 1, 0. Yeah, the other way around. 1, 0. X values first, the x value of 1, y value of 0. Well, what about in the second graph? Same thing. 1, 0. Now what we're going to do is we're going to talk about what happens when you take this graph and you do it like we have done with some other graphs before. You move it left, right, up and down, reflect it, flip it around, that kind of stuff. We're not going to spend a lot of time doing that, but we're going to do a couple of examples. Okay? So the first one is just a basic graph of what it should look like. If you have the graph g of x equals log base 8 of x, which one of these is that going to look like? The first one or the second one? The first one. Why? Yeah, because a, which is 8 in this case, is greater than 1. We have a base that's greater than 1. So this graph is going to look roughly like this, crossing here at 1. And we're going to identify a few features of the graph. The first one is the vertical asymptote. So what's the vertical asymptote for this graph? Yeah, x equals 0, same as before, no differences. We talked early on in this section, like the first slide, about domain and range, and now you can actually see it on the picture, right? What's the domain for this graph? Right, 0 to infinity, and notice they're parentheses. We're not equaling 0. There's an asymptote there. What about the range? Yeah, everything. Negative infinity to infinity is on my range. Now we're going to take this log base 8 of x and we're going to manipulate it. We're going to do something where we shift it somehow or we stretch it somehow or we do something to it, and this is the one we're going to do. There are 3 ways in which this graph will be different than the one before. So jot it down and we'll talk through the differences. Working from left to right, what's the first thing you notice that's different about this graph, the equation of it? The negative at the beginning. Did you guys see that? The negative? Okay. How does the negative outside of an equation change it? This is like we talked about like a month ago. There's some kind of a reflection, right? And you have to remember, does it reflect around x? I mean, that was y. I'm putting my hand there. Is it reflecting around y, like this, you know, reflects left to right, right to left, or does it reflect around x, up and down? It's x. Yeah, some of you are even doing the motions in the hair. It's an x reflection. Everything that was a positive 5 value as coming out of it will now be a negative 5 value, so it'll flip it down. So this is a reflection that's over the x-axis. All right, the next piece has a -2. What is that -2 gonna do? Good. This is a right or left shift or a horizontal shift. This will move it right 2. And how about that 3 at the end? Up 3. Good. Now, we didn't talk a lot about order of operations of these, but it's the same as order of operations of, like PEMDAS, right? Please excuse my dear Aunt Sally. We move from the inside to the outside of things as we're simplifying. So the innermost piece of this that's being affected is the shift right 2. So if I were to take this graph over here, and I were shifting it right 2, it would also shift the asymptote, correct? Where would my new asymptote be? At x equals to 2. And in fact, I can write that down even as I draw it. My asymptote will be at x equal 2. So I'm going to draw a vertical line in here at x equal to 2. And there's my vertical asymptote. Now that also shifts over what was the x-intercept, right? It was at 1, now it's at 3. We're not done because we're still moving some pieces around, but right now that shift would move it over to 3. Next piece, moving from the inside out, is to move on to the negative in front, right? Multiplication before the addition at the end. Multiplied by -1. So I'm going to take this graph, I'm going to flip it upside down. Now think about over here. The first graph's the one I'm basically working with. If I flip it upside down, what's it look like? The second graph, right? So that's sort of interesting. Because of that negative reflection, I actually have a graph that's going to end up looking like the second graph on this slide. Okay? And then the last thing I'm supposed to do is I'm supposed to shift it up 3. So what was the x-intercept is now at 3, if you will, in the air. So I've actually got a 0.33 plotted on my graph, and the graph is decreasing. Something like this. I already identified the vertical asymptote. What's the domain for this graph? Close. Yeah, 2 to infinity. Right, we can't equal the 2 because there's an asymptote there, but we can get really, really close to the asymptote. So it's 2 to infinity. What's my range? Yeah, negative infinity to infinity. Okay, any questions on that? Yes?
Why is it 3 on the x and the 3 on the y? I don't understand why it's 3.
Previously, I had the value here at 1, and I shifted it right 2 because I had a plus, this -2 right here, moved it right 2. So I moved that 2 to the right, which would put it at 3. Yeah. And it doesn't end up being, like you said or noticed, it doesn't actually end up being the x-intercept because then I have to move it up 3. But it still is a point that I can for sure plot that I know where exactly it is. All right, last set of questions we're going to take a look at are actually solving equations. We simplified expressions by changing them into equations before. This is very similar. We're going to actually solve equations to begin with on this problems. Now, in particular, the goal in solving an equation is to somehow get x in a position where it's either able to be identified or be able to be solved as x equals. And x's, generally speaking, inside of the log in either of those two spots, either the base, where the 4 is right now, or inside of the log, where the x is now, have to be changed. And you guys know how to change them because we've done that all morning this morning at this point. How do I change this equation into something that's easier to work with? What would it become? Somebody tell me what it become loud in a voice I can hear.
4 to the 1/3 equals x.
Thank you. Very good. Thank you. 4 to the 1/3 equals x. Right? We start with the 4, and we draw our arrow around, and we land at the x. 4 to the 1/3 equals x. Now, the reality is 4 to the 1/3 equals x is actually a legit answer, and it could stop there. It's probably not the most familiar or comfortable way of writing it that you've ever encountered. Do you remember another way of expressing 4 to the 1/3? Yeah, good. So we could also write it as the cube root of 4. And in particular, if it hadn't been a 4, but it had been like an 8, we would simplify that, right? We could do the cube root of 8. Cube root of 4 doesn't have any way of being simplified, so at that point we're done. But because we couldn't simplify it, those are both actually equally simplified or written out answers. Either of those are fine. B is perhaps the most awkward problem of the day. Yeah. And the reason it's awkward is because if you'll remember back in section 4.1, every problem that we did had the ability to have the same base on both sides, right? Like I was able to get base 5 on the left, I could get a base 5 on the right. And this problem, you can't do that. I mean, you can't. I've got a base 5 on the left, and 12 has no way to be written as 5 to a power. All right, so what do? Well, we're going to change it into a logarithmic form, and I'll show you how you can solve it from there, okay? So, how do you change this into a log form? What would it end up looking like? I'll get you started. Log. Base of 5. What would come next? The 12 would come next. Be careful. So if you're thinking about drawing your arrows, you have to go to the other side of the equation first, and then you'll land on the exponent, which is the 3 minus x. Okay, is everybody good with the rewriting step on that one? Because honestly, if you mess up with the rewriting step, you can't do anything else correct. Everything else falls apart. So the rewriting step is super important. Okay, now, like it or not, this isn't a very pretty number, but it is a flat-out number on the left-hand side. It's a decimal approximation, and we can figure out from our calculator what it is. We will actually do that at the very end of this problem just so that we have a numerical value to write down. But it is a number on the left. And the reason I know it's a number on the left is because there's no variable there. Do you guys see that? You may not like the word log written in the middle of it, but it is a number. Okay? Now, our goal is to solve this for x. So what do I have to do next to get x alone? I need to move the 3. How would I move the 3? Subtraction, right? So I'm going to do minus 3. Be careful. This minus 3 does not get subtracted from the 12. 12 is inside of a log and 3 is not. It's like having something underneath a radical and something not. You can't combine them. So it might help to even write it at the beginning just so that you're not going to accidentally do that, and write as negative 3 plus log base 5, 12, just so that you don't accidentally think that somehow the 12 and the 3 can combine. Okay, I've got it solved for negative x. What do I do next? Divide or multiply by negative 1. You got it. So all the signs are going to change. This will become 3 at the beginning, and then minus log base 5 of 12 equals x. Now again, you may not like the way that that looks, but what's on the left-hand side is the 100% accurate answer. It's not a very pretty answer. It looks weird, right? Now, the best you could do otherwise would be to use your calculator to get an approximation, and we'll do that too just so that we can see what would happen. But be very careful on the directions. If your directions say find the exact answer, you stop there. If they were to ask you to approximate, then you would go on to what I'm about to do next. Does that make sense? We'll do it to 3 decimals. If there's directions given to you, they'll tell you how many decimals they want you to approximate it to. But let's take a look. If you were using your calculator to do this, we would rewrite the log base 5 of 12. How? Good job. Log 12 over log 5. So if you grab your calculator, it can tolerate, most of your calculators can tolerate, just put this in from left to right, 3 minus log base 12 divided by log base 5. And I don't have an answer written down for an approximation for that, but one of you guys is going to tell me what you get. I'm just sure of it. .456, and I think now that you just said that, I think I heard somebody say it really quietly before. Anybody get anything different? Awesome. If you did get something different and you just don't want to say it out loud, let me know afterwards and we'll see if we can figure out what your calculator's doing, okay? Okay, a couple more examples. C looks really weird. It's really not that hard, but it just looks so weird because it's got all the fractions involved. I mentioned earlier, and I'll mention again, the fact that the x is in the base of the log tells you you've got to change it into exponential form. Okay, we need to get the x out of that location. So how would I rewrite this in exponential form? Excellent. X to the 4/3 equals 1/16. Okay, how do I solve then for x? There's several things I could do. Anybody have an idea of what you might want to try as your next step? Okay, then I'll give you a suggestion. How's that sound? The other word? Okay. What we really want to do is we really want to raise this to a power that cancels the 4/3. So what power would cancel a 4/3 power? 3/4. Okay. I'll deal with the right-hand side and how weird that looks after I do that in a second, but that gives me the x that I want on the left. I'm just raising it to the power 3/4 to cancel. Now you guys know what the 3 and the 4 mean. What does the 3 tell you? Cubing it, right? Multiply it by itself 3 times. What does the 4 in the denominator there tell you? Not quite. What if I just had, I don't know, let me just do this right now. What would 2 to the 1/4, what would I do? It'd be a 4th root, right? I mean, the power that's the 4 in that denominator is a root. So I'm going to actually rewrite this with roots and exponents. So the 4 is the 4th root of the 1/16, and it has an exponent of 3. We've done that before, but it's been a while, I know. Now, sometimes it's easier to do the cubing part of things first, and sometimes it would be easier to do the 4th rooting part of things first, and it just depends on the number. On this particular one, the 4th rooting is easier because there's a simple, easy 4th root of 16. If that weren't the case, we might want to cube something, but I don't know about you, but I don't want to cube 16. That becomes a much larger number that I don't have as much familiarity with, an easy way to do things with. So the 4th rooting is easier to do first on this one. What's the 4th root of 16? 2. What's the 4th root of 1? 1. So the 4th rooting process on this one becomes the 1/2, and I still have it raised to the power of 3. So I kept my numbers small because they're easier to work with. What is 1/2 to the 3rd? 1/8. Very good. All right, D is a fun one. And I don't say that meaning it to be mean like it's hard. It's actually very easy. But it looks like it's hard. I mean, it looks really messy. But here's the cool thing. Do you remember when we worked with the problem B over here? That one right there? That at some point we got to a place where we were looking for the bases to match. We wanted something to look the same so that we could focus on the stuff that didn't look the same, right? That's our goal. And that's much the same goal that we have over here on D. Part of this looks the same, namely log base 3 on both sides, right? And because that looks the same, we can ignore it and focus on the part that doesn't. In order to get this to actually be equal, the parts that are inside of the logs also have to be equal. So we aren't canceling. Please do not mark them out. That's not appropriate. But we are ignoring them. We're saying these parts already match, which means that my attention can now be turned to the parts that don't. This says 2x on the left, and it will have to equal the 24 minus x squared on the right. So our log equation very quickly turned into a quadratic equation, which we know how to solve. And in fact, if we move everything onto the same side, it gets even better. So I'm going to move everything to the left-hand side. I'm going to add my x squared and subtract the 24. So I have x squared plus 2x minus 24. And that's so lovely because it even factors. So how will this factor? Yeah, somebody's whispering in. I heard it. X plus 6 and x minus 4. You got it. What would I do next? Set them equal to 0. Okay, so what does x equal? Okay, now the answer to the quadratic equation is that x equals -6 and x equals 4. But we didn't start out with a quadratic equation, we started out with a log equation, right? And we need to make sure that these answers still work in the log equation that we actually began with. Now, think about your graph over here. What is the domain? What x values are you allowed to have inside of log? Positive, right? The domain is the positive values. I guess we wrote it right here. Oh, this one's a good one, actually. Our domain is positive values. So when we're looking at this equation over here, the input inside has to be positive, which means x can't really equal -6, can it? Because then I would be trying to put in -12 into the input on the left-hand side. So while it was a solution for the quadratic equation, it doesn't actually end up working for the original equation we started with. But x equals 4 is fine, right? I can put in 2 times 4, that's 8. On the right-hand side, if I have 24 minus 4 squared 16, that's still positive, I'm good to go. Grab your calculator as the last thing we'll do today. I want you to just see what happens if you were to happen to forget to check the domain and you tried to see in your calculator, does it work? I would like for you to type in just log, it doesn't matter about the base 3 right now, just type in log of some negative number, log of -16, log of -432, log of -1. What does your calculator tell you? Usually they tell you domain error or some kind of an error. So if you're being watchful or mindful or you're checking yourself with your calculator, that's also another way to catch in case you accidentally think something's an answer that's not.